Okay, welcome AP to Chapter 10, the podcast on liquids and solids and intermolecular forces, the forces that exist between the molecules. Okay, this chapter is going to uh, deal with the forces of attraction that exist between molecules and how these forces determine a substance's phase or state of matter. Okay, remember back in chapter 5, we discussed kinetic molecular theory, okay, and how gases behaved ideally. And remember, at high temperatures and low pressures, that's the most idealistic setting and to get the perfect gas behavior. And that's because real gases then do not have intermolecular forces, the forces between the molecules, uh, they do not come into play. And so that's why they can exist as a gas and behave ideally. And so in this chapter, we're going to focus basically on liquids and solids. Okay, so we're going to start out with the idea that we have two types of bonds. Okay, we have um, intramolecular forces, and that's your force that exists within a molecule. And it happens because valence electrons are being shared between the atoms. Okay, so for example, water. We're going to use water a lot. Okay, so I'm just going to draw it quickly here. Now there's its Lewis structure. Okay, this is your intramolecular force. Okay, that's your force within the molecule. And then we have intermolecular forces. Inter meaning between. So these are your molecules that exist between uh, each substance. Okay, and there's three basic types: dipole-dipole, hydrogen bonding, and London dispersion forces, or just dispersion forces, or LDFs if you prefer. And the intramolecular forces are going to be way stronger than the intermolecular force. Think about trying to take some ice and melt it versus trying to break the hydrogen and oxygen bond completely and get individual hydrogen and oxygen atoms. Okay, takes a lot of energy, like a current. Okay, a current, electrical current. Okay, so we're going to talk about each of these three types of intermolecular forces uh, individually. Okay, and so we're going to start out with the dipole-dipole, but here's a quick visual to remind you, remember how to read these pictures. Okay, so this was showing the dipole, the negative and positive end of water. Okay, and so the two lone pairs here on water, now the attraction here, the negative end and the positive end, so this is happening between the molecules. Okay, that's your intermolecular force, or IMF to be shorter. It's easier to write too. Okay, so which are stronger? Quick check. Hopefully you said intramolecular force, because we know it takes a whole lot more energy to break the atoms apart than it does to separate the individual molecules. Okay, so intermolecular forces are the forces to be thinking about when anytime you have a question on phase changes. Okay, so what's happening is you're not breaking apart atoms, you're breaking those intermolecular forces. Okay, the forces within are not breaking. It's the forces between that are breaking. All right, here's a schematic, a visual model, if you will, of solid, liquid, and gas. And then our intermolecular forces are going to increase as we go this way. Okay, so stronger forces between the molecules, weak forces between the molecules. And then remember, idealistic behavior, high temperatures and low pressures, then intermolecular forces don't come into play at all. Okay, so to have your phase change now, energy has to be added. That means it's an endothermic process. Okay, and you get greater kinetic energy, greater molecular movement, and disorder begins to become more and more apparent as you go from solid to liquid to gas. Okay, so density is also affected or changes depending on the phase of the matter. And here's an example with water. Remember, we always used to say water has a density of 1, but if you want to get really exact, mass per volume here, the solid contracts with water, expands with water. That's why you put a can of soda or something in the freezer, it wants to explode or break out of its container because the volume changes. So these densities are our relationship with the volume changing in the substance. Okay. All right, so we're going to start out with the first intermolecular force, and that's the dipole-dipole force. Okay, so polar molecules have dipole-dipole forces because they have dipole moments. Okay, so let's see if I draw my water again here. Reminds you of a dipole moment. Okay, so overall, if we add these vectors together, we would have a dipole moment going this way. Okay, so this is a polar molecule, so therefore it has forces of attraction between the molecules, and it will have dipole-dipole intermolecular forces. Now I probably shouldn't have drawn water because water has an even stronger dipole force, and that's hydrogen bonding. I should have drawn something that was polar that didn't have hydrogen bonding. Okay, I want to think of CO2, but then as I think of CO2, I remember that it's not polar because of its symmetry. See, the dipoles cancel, but a dipole-dipole force will exist between polar molecules. Okay?
Bonds between atoms with different electronegativities have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole. For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as a result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds, therefore it is a polar molecule. When polar molecules such as sulfur dioxide are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces.
Okay, so that was a quick review of the what makes a substance polar or not, and then the type of force they would have, of course, is dipole-dipole. Okay, here's hydrogen bonding.
Some polar molecules have unusually strong intermolecular attractions called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water, with 2 hydrogen atoms and 2 unshared pairs of electrons, can form 4 hydrogen bonds per molecule. In ice, hydrogen bonding leads to a tetrahedral arrangement of water molecules around one another, forming 6 membered rings that leave open channels through the ice structure. In liquid water, the tetrahedral arrangement is not fixed because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom.
Okay, so hydrogen bonding is a type of dipole-dipole, but it's a stronger dipole-dipole. And that's because of this very electronegative atom that the hydrogen is bound to. You guys remember the movie E.T.? Okay, good way to remember this. Phone home. Remember that? Okay, maybe I'm dating myself. Okay, so it has to do with the electrostatic attraction that exists between the lone pairs. Okay, and you saw that visual there in the previous slide with the video clip. Okay, and so now
In solid carbon dioxide, dry ice, nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
okay, so London dispersion forces tend to be the weakest forces of the 3 types, although you have to be careful because as the molecule gets larger and the mass gets greater, um, London dispersion forces can tend to be greater than dipole-dipole forces. So you have to keep that in mind. But all it is it's because we get an instantaneous dipole just due to the electrons in motion, accidentally, forming dipoles, and these happen in all substances, okay? And so we know nonpolar substances have London dispersion forces. We know polar substances have dipole-dipole forces, and if the polar substance is hydrogen bonded to F, O, or N, then you have hydrogen bonding. Okay, so we want to know about intermolecular forces because this is what determines the type of melting and boiling point you're going to have. The greater the intermolecular force, the stronger it is, the higher the melting and boiling points. Okay, so I'm going to insert a clip here now just showing some different types of questions you might encounter dealing with molecules and melting and boiling points. And so we'll practice thinking through intermolecular forces. Okay, here's an example where you have to look at a couple of substances and try and determine which one has the higher boiling point. And again, the thing to be thinking about here is intermolecular forces. Okay, so let's start out with the first pair here. CO2, carbon dioxide, versus NH3, ammonia. Okay, we've got we've got a nonpolar substance here because CO2, while it has polar bonds, its symmetry makes it unpolar. So LDFs here, London dispersion forces. Okay, now we've got a polar molecule. Okay, but look at what's involved here. Nitrogen and hydrogen, highly electronegative. molecule here. So not just dipole-dipole, but actually hydrogen bonding. So higher boiling point, ammonia. Okay, hydrogen bonding going on there. All right, let's try another one. We've got an alcohol, and then we've just got an alkane. 1, 2, 3. Prop. So we've got propane versus propanol. Nope, 1, 2, ethanol. Okay, ethanol, propane. Okay, which one has the higher boiling point? Okay, well, here we've got an LDF. No polarity going on, symmetry. And then we've got an alcohol that's got hydrogen bonding. So what are you going to say? There's our hydrogen bonding again. So higher boiling point. Okay, and then sodium fluoride versus hydrogen fluoride. What kind of substance do you have here? This one's ionic. Okay, so you've got electrostatic forces going on. Okay, so we've got, I had something pop up there, so I had to stop. Sorry about that. So we've got an ionic substance versus a molecular substance. So which one already, we don't even have to think about intermolecular forces. Ionic is going to be stronger intermolecular forces than our molecular substance. Okay, so much higher boiling point than hydrogen fluoride. Okay, so there was just a few samples of the type of questions you're going to get, and you'll practice more in your small groups. Okay, here's a visual, a graph showing the different families, okay? And so as we go across period 2 there's nitrogen, okay, well there's carbon, and there's nitrogen, and then we should have oxygen, and then we have fluorine, okay? But oxygen is way up here. And why is that? Well, these three deal with hydrogen bonding, but the reason why water's boiling point is so much higher is because water has two sites for hydrogen bonding because of its structure. And so that gives it an even greater boiling point. And so that's this graph is giving you that visual. Okay, quick check. Which one's going to be stronger in terms of their intermolecular forces? This diatomic molecule of nitrogen or water? Hopefully you said water because of the hydrogen bonding versus London dispersion forces. Right? So of course, which one has the higher boiling point? Well, water, of course. Nitrogen or the diatomic here, nitrogen, is a gas at room temperature. So that clues you in right there too, how weak that intermolecular force is compared to water being a liquid at room temperature. Okay, another quick check. C2H6O, draw the two Lewis structures for this. And so here we have drawn an alcohol, okay, and here we have drawn an ether. This is dimethyl ether, and this is ethanol. And it asks you to compare the two, the boiling points of the two molecules. And so, which one's going to have the higher boiling point and why? Well, it should be ethanol because this has hydrogen bonding versus dimethyl ether, which is a bent molecule, which is polar. So this has just the dipole-dipole. Okay, so this is dipole versus hydrogen bonding, so higher boiling points. Okay, so Again, when you're asked these kind of questions, you're thinking about the intermolecular forces, the IMFs. Okay, which gas would behave more ideally? Okay, carbon monoxide or nitrogen? This is going to be a polar molecule. This one's a nonpolar molecule, so LDF, dipole. This one should behave more ideally. Why? Because it's a weaker intermolecular force. So when they collide, their collisions are, elastic. They just bounce off. That's a more ideal behavior versus the carbon monoxide. Okay, so now when we get talking about liquids, okay, we're going to look at three different properties that liquids have. One of them is surface tension, and that's the resistance of a liquid to increase its surface area, or if we try to say that a little simpler, it means can that liquid form like a skin over its surface, a little skin type invisible layer, okay? Or capillary action, that's a second property, and that's a liquid's ability to rise up in a narrow tube. And then viscosity, that's a liquid's resistance to flow. These three properties are directly related to the intermolecular forces that exist within them. Okay? And so let's start out talking about surface tension. Okay? So let's see if I can draw this now. Okay, so let's pretend this is water. Okay, so these little circles are H2O molecules. Okay, so this is the surface of the water. And then here's a little bit below the surface. Okay, and so we have forces between the molecules, okay, in three directions, but not up here. There's no force going on up here because there's no molecule up here. So these three forces are pulling very tightly on each other. These three molecules, they have that hydrogen bonding going on between them, and they're pulling tightly. And so they're causing this surface to form because of the tight packing of the molecules. Okay, and so you've maybe seen on a swimming pool or on a lake some of the little insects that skitter across, okay, and that's because of the high surface tension the water has. Okay, that's also why water beads up on a waxed car, or why raindrops fall and they fall in drop form because of this surface tension concept, these high intermolecular forces that the water has. Okay, so the larger the intermolecular force, the higher the surface tension tends to be. Okay, let's go on to second property, capillary action, the ability of a liquid to rise in a narrow tube. Okay, capillary action is dependent on cohesive and adhesive forces. Okay, if you want to get the liquid to rise in the tube, that liquid needs to have an attraction for the walls of the container. A larger attraction for the walls of the container than the attraction for itself. Okay, so cohesive forces are the intermolecular forces within the liquid, and the adhesive force is the force between the liquid and the container itself. So let's compare two substances. Let's compare mercury and water, mercury being nonpolar and water being polar. Okay, and so here's liquid mercury, and notice that its meniscus within a graduated cylinder is convex, meaning it curves downward because it doesn't have a force of attraction because it's nonpolar. It's not attracted to the container surface, okay? It's more attracted to the forces within itself. So which force dominates? The cohesive force, and that's why we get this downward meniscus, okay? Versus water, water gives us this upward or concave meniscus because water is highly attracted to the surface of the container versus the forces within itself. So which force dominates? Well, the adhesive force dominates. And that's why you get the two different types of meniscuses between those two different substances. Okay, and lastly here is viscosity. Viscosity is a measure of a liquid's resistance to flow. Okay, and so, of course, the greater the intermolecular force, the tighter the molecules hold together, and then the more viscous they become, or thicker they tend to become. So maybe you've experienced this if you've ever gotten to put oil into a car, or if you've compared maybe some different ketchups. The, 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 um, the more expensive the ketchup, the thicker the ketchup seems to be and the greater the viscosity versus maybe a little cheaper ketchup tends to be more runny, so it has a lower viscosity. And so again, related to intermolecular forces, higher intermolecular force, higher viscosity. Okay, I want to insert another clip having you practice with the properties, the different properties that liquids have. So I've picked one where you're dealing with viscosity. Okay, so looking at these three substances, which substance has the greatest viscosity? So again, viscosity deals with intermolecular forces. So viscosity means resistance to flow. So you're thinking about which substance is thicker, which one doesn't flow as easily. Of course, the greater the IMF, the higher the viscosity. Okay, so let's look at each of our substances. Hydrogen sulfide. What do we got there? Well, I'm going to draw the Lewis structure, and it is bent. Okay, so that makes it polar. So if it's polar, we have what kind of intermolecular force? We have dipole-dipole. Okay, now I have hydrogen fluoride, polar molecule. Okay, so what do we have? Oh, we have dipole-dipole again, but specifically it's a hydrogen bonded to a fluoride ion, very electronegative, so we are looking at a hydrogen bond, so the stronger case of the dipole-dipole. So we're increasing in viscosity. And then what do we have here? Hydrogen peroxide. Okay, we've got 6 valence, and 2 valence, so we've got 14 electrons we're dealing with there. Okay, so I'm going to draw this structure. Oxygens have to be in the center because hydrogens can't. Okay, and so there we have it. 2, 4, 6. So I've used 6 electrons. I got 8 left. 1, 2, 3, 4, 5, 6, 7, 8. I had to put them on oxygen because the hydrogens were already fulfilled. And so there we have it. So again, it looks like we're looking at another polar molecule. Okay, so all 3 polar. But this time, we've got hydrogen bonding in more than one place, more than one site. So we've even got a greater hydrogen bond going on than here. So greatest viscosity is going to belong to this hydrogen peroxide. Okay, let's try another one. Let's see. Let's try one with surface tension. Okay, so which substance would have the lower surface tension this time? So again, the greater the IMF, the higher the surface tension. So the greater this is, the higher the surface tension is. Okay, but we're going to look at the one that has the lowest surface tension, so we're going to look for the weakest intermolecular force. Okay, so carbon tetrachloride. Okay, so we have polar bonds. but because of its symmetry, it's a nonpolar molecule, so we're looking at London dispersion force. Okay, carbon tetrafluoride. Okay, even stronger polar bonds, but because of its symmetry, London dispersion. And then carbon tetrabromide. Okay, so now how do we decide? Because they all have LDFs because of its symmetry, nonpolar, so nonpolar, 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 so all LDFs. So now how do we decide? Okay, what you have to think about now is the size of the molecules. They all have carbon. The different molecules are the ones on the end. So let's get our periodic table. So fluorine, chlorine, bromine. Remember the trend goes this way. Bromine being the bigger molecule, this is going to be the stronger force. So this one's going to have the higher surface tension. Okay. Fluorine now being the smallest molecule, it's going to have the weakest. Okay, so there's two problems dealing with the properties that liquids can have. So you had a chance to practice some more intermolecular force questions. Okay, so here ends the first podcast for Chapter 1.